Alright, kiddos, one more optimization problem coming at you for now. This is number 4 from the problem set we've been working on. And we have a big can. Actually, it's probably more like a cylindrical tank based on its size. So we'll call it a cylindrical tank. And it's going to hold 20 pi cubic meters of water. We know that the top and bottom are going to be $10 a square meter. And the side, the lateral area, is going to be $8 a square meter. We're trying to just find the radius and height of the most economical can. And of course, most economical can means minimize the cost, right? So the essence of this problem comes down to this. We want to minimize the cost given or such that it holds 20 pi. Now that means the volume is going to be 20 pi. Oops. Okay, that's the essence of this problem. We're building a can, minimize the cost, and it has to hold a certain volume, 20 pi cubic meters. Okay, that's the essence of this problem. Let's get a little bit more specific. So here's a diagram. It's nice to have big tanks, R's and H's and diagrams so we can see what's going on. So we have 2 dimensions, R and H, we want to find that are going to minimize the cost while holding the volume. We need to be more specific now regarding both the volume and the cost formula which we want to minimize. So let's start with the volume first because it's easier. And a volume of a cylinder is going to be the area of the base, which is pi r squared times the height. Okay, so and I can get rid of that. So this is kind of my constraint, my limiting condition, my parameter that has to be satisfied. All right. What we want to do is minimize the cost, so I have to come up with a way to quantify that. So the cost tells me that, well, the top and the bottom are $10 per square meter, right? To find the area of the top and bottom, they're both circles, so it's going to be $10 times 2 pi r squared, right? Pi r squared for the top, pi r squared for the bottom. That makes 2 pi r squared times $10 a square meter, plus $8 for the sides, right? And that's called the lateral area. Now you may or may not remember the lateral area of a cylinder is 2 pi r, which is the circumference of the base, times the height. The lateral area essentially ends up being a rectangle when you unfold it. 2 pi r h, right? And let's clean that up a little bit. So basically what we want to do is we want to minimize the cost, which is 20 pi r squared plus 16 pi r h. Okay, such that the volume pi r squared h is 20. There's the problem. Okay. Now, we can't minimize the cost yet because although we've quantified it, there are too many variables. There's r's, h, and c for cost, or 3 variables. So it ain't a function. What we want to do is get rid of that h right here. All right, let's get rid of that. And what we're going to do is we're going to leap over to the given to help us do that. Right? And so if I isolate h here, I get 20 pi over pi r squared, which is 20 over r squared. All right? Now what I'm going to do with that 20 over r squared, I'm going to plug that right in here into my formula, which I want to eventually turn into a function. I'm going to do it right now. So the cost then becomes 20 pi r squared plus 16 pi r times h, which is 20 over r squared based on our parameter. Okay. Now what I've done is now I have a cost function. It's a function of r and only r, not cost a function of r and h, or relation of r and h. So what I can do now is clean it up, take the derivative to find the minimum value. All right, so I'm going to clean it up first. 20 pi r squared plus r over r squared just leaves me with 1 r in the bottom. So I get 320 pi over r, right? And over r is the same thing as r to the negative 1. And I'm going to write it like that because it's going to help me see how to differentiate that piece a little bit better using the power rule. Okay? Here is my now function, right? Which I can then take its derivative, set it equal to 0 in order to help me find the minimum value. Okay? So I'm going to take the derivative. 2 comes down, multiplies by 20 to give me 40. Pi is a coefficient, r times r to the first, right? Minus, the negative comes down, 320 pi r to the negative 2. Now I'm going to write it as such. R over r squared, it's the same thing. And of course I took the derivative because I want to now set it equal to 0, because it's going to help me find those critical points, points at which I will probably have a minimum value or max in general. So I'm going to solve this particular quadratic. Actually not quadratic, that's wrong. Ends up being cubic. But let's multiply everything by r squared. Okay. So what happens is if I multiply everything by r squared, I get 0 equals 40 pi r cubed minus 320 pi. All right. I'm going to subtract 40 pi r cubed from both sides. And now I'm going to divide by negative 40 pi. So essentially what I get is r cubed equals 8. Oh, nice solution. Right? If r cubed equals 8, that means necessarily r has to be 2. Okay? Now in the past, what we've done after this is we have put 2 into our chart, the derivative of the cost function, and made sure that around 2 or to the left of 2, since we're looking for the minimum, the derivative will be negative, and after 2 will be positive, which will mean at r2, the cost function has a minimum. Okay, we're not going to do that anymore. We're just going to assume that's the correct value. Okay, so no. Now all I have to do is take that r equals 2 and answer the question. So I know r is 2. My optimal radius of this big tank is 2 meters. Okay, I found that. So what I need to do now is find the height. And since I know that my little height over here is 20 over r squared, right? So if I take 20 divided by 2 squared, I end up with 5. Okay? And now if I want to get the optimal cost, all I have to do is in my cost formula plug in an r for 2 and a 5 for h. Okay? And I'll leave that for you to do. Actually, I'll do it. I got enough room here. And so the answer is the ultimate cost will be 10 times, where am I here? Here's my cost function formula. So I'm going to plug a 2 for r, so that becomes 4 here, times 20, that's 80, so I got 80 pi so far, plus 16 pi times that r, which is 2, times the h, which is 5, of course the optimal r and h, so 2 times 5 is 10, times 16 is 160 pi, so that gives me 240 pi. Right, so here is the optimal dimensions and my minimized cost for producing that optimal Hank. Alright, so rewind this if you need to. Have a great day, and we'll keep plugging. Bye-bye.